Hi, everyone. Welcome to the second day of ACHEMA Pulse 2021. It is my pleasure to introduce Peter Zornio, Chief Technology Officer at Emerson. He is going to talk about 3 core technologies to re-architect automation. If you have any questions, please use the panel on your side. With this, over to you, Peter.
Hi, thank you very much, Lorena, and welcome everyone to ACHEMA Pulse. I would love to be there physically in person, but circumstances being where they are, it's not quite possible. So instead, I'm coming to you here from our integrated plant environment that we have in Shakopee, Minnesota. We test out a lot of technology here, and we train a lot of customers in this facility. Today, as Lorena said, I'm going to talk to you about 3 of the big technology changes that we see coming that we think are going to dramatically change the automation and operations environment. So if we start by looking at the way things are today, in most plants, you typically have a control system, PLCs, DCS systems. Some plants have safety systems if they have hazardous processes, a variety of different field instruments, and a variety of software applications that go on top of those automation systems. Those software applications are typically running at the plant level on Windows computers. And of course, the control system is also typically on the facility, and it's connected to the field devices with a very wide variety of different protocols today. One of the big changes that's coming, and one of the technologies I'm going to talk about, is advanced physical layer. And the advanced physical layer is going to bring Ethernet to all those field devices, unify those field devices with a control system in a much stronger way, and just unleash a whole bunch of new data from the field. The next technology change I'm going to talk about is cloud. So if we look at cloud today, yes, IT departments in most customers are using cloud. In the enterprise world, cloud has become very popular and grown very fast. I'll have some data where I'll show you that. But it's typically been for those IT and enterprise applications. And it's connected to automation systems, or data centers inside the customer's facility are connected to the automation systems with a number of carefully engineered bespoke connections. One of the things we see changing is cloud coming down into more and more automation and operations applications. And we also see SaaS models, the models where instead of hosting the applications yourself, the vendor of those applications, such as us, Emerson, will host those, and you will just subscribe to them in a SaaS kind of model. Or you may also tie into our connected services, where we are analyzing data for you and telling you what's going on. So cloud is one of the second technology changes that I'll talk about. The third technology change I'll discuss is really more of an entire architecture than it is a technology. And that's what I like to call the enterprise OT system. So typically, we've always counted on the automation system as the thing that pulled in data from field devices. But with digital transformation, what we see happening now is a whole new architecture being built, outlined here in gray, where new field devices, new edge devices are all generating data and doing analytics down at the plant level. And we also see new aggregation technologies for tying that together that we call the OT data lake. And that is also becoming the way to shepherd all that data, as well as the existing automation data, into the cloud environment. So the enterprise OT system is the third, more than a technology, let's call it new architecture that I am going to discuss today. So these 3 technologies are going to dramatically change and shift what the overall operations architecture looks like over the next coming years. Let's start and look at a little more detail at Ethernet APL. So traditionally in the process industries, the most common connection from field devices to the automation systems is 4 to 20 milliamps. And often it's accompanied by the HART protocol that carries some digital data. Then there's also a number of other protocols that have been used, typically on Ethernet today, such as Profinet or Ethernet IP or or even Modbus TCP running the old Modbus protocol over Ethernet. Ethernet is great. It has fast communication, high bandwidth, everyone uses it. It's easy to integrate IT and OT data, but it has big barriers when you try to use it in process facilities. First of all, Ethernet does not support a simple two-wire communications. You need special Ethernet cable. It has limited distance, and in most cases, it requires separate device power. So it's not nearly as simple to install as the two-wire 4 to 20 and other analog connections that we're used to for field devices. It's also not capable of being intrinsically safe, which is an important safety requirement in many chemical facilities. Ethernet APL is going to change all that. Ethernet APL is a new physical layer that runs all those existing Ethernet protocols, but runs them over a physical infrastructure that meets the installation requirements of hazardous processes. Ethernet APL will be much faster than protocols such as HART or Foundation Field Bus. It'll be 10 megabits. It will still support, however, that two-wire simple communication, power on those two wires, and the field device part will run for 200 meters from the nearest junction box that contains an Ethernet APL switch. So Ethernet APL is a way to extend the plant Ethernet architecture and plant Ethernet network into field devices in an intrinsically safe way while still providing power. Now, it's not a new protocol. It's going to still run all the same protocols that we run on traditional Ethernet. If we think about, who's going to be involved in Ethernet APL, well, first of all, the standards themselves have been defined in International Standards Committee, the IEEE, or the Electrical Engineering Group, and the IEC. But there's also a consortium of vendors that we call the Ethernet APL Working Group, whose names you can see here. Emerson is a member, that are working together to help bring this new technology into the industry. They're also the group that's working on the intrinsically safe definition of what this protocol, of what this field level technology will look like. There's also a number of protocol organizations that are part of this working group, and you can see their names there as well. Because again, Ethernet APL is just a physical layer. It's just the communications media. It's not the protocol. And all the same protocols that we see on Ethernet, we will find on Ethernet APL. Now, why would you use Ethernet APL? Well, as I mentioned earlier, one of the biggest and most attractive features is the amount of data and the speed at which you can send that data. The benefit of having that is going to vary greatly depending on the type of device you're connecting and the type of information that's in that device. So what I've done on this chart is I've listed a number of the traditional kinds of devices that you will find in a process facility today, from general order to which I think they're going to benefit the most and have the most kind of data to offer on Ethernet APL, to the ones that maybe just consistency in having a single type of architecture is going to be the biggest driver for APL. We have a number of devices here, the ones at the top, such as Coriolis meters or gas chromatographs, that are already using off-the-shelf Ethernet where they can, where they're in facilities that don't need intrinsic safety and they can meet the distance limitations, because they have a lot of data, and that ability to bring in all that data is extremely important for those kinds of devices. What I expect to happen with APL is that middle band of devices that you see there, things such as a radar level or a multivariable transmitter, a digital valve positioner, those are the devices that are really going to benefit from Ethernet APL, from the ability to have this high-speed data pipe in an intrinsically safe manner, but with the same ease of installation that we have today with our 4 to 20 connections. As we get to simpler devices like pressure and temperature transmitters, they have intelligence, they have data, but not to the same quantity. And frankly, the HART protocol has worked pretty well over 4 to 20 for those devices. But as we move to having APL kind of widely available and widely installed in a plant, it's going to make sense to bring those to APL as well and have a consistent architecture, as well as we'll think of, like we always do, new features and capabilities to take advantage of that new bandwidth and also the new power that Ethernet APL is going to bring that will enable us to run more functions and have more memory in those devices. There is a class of very simple device that I think will probably never directly talk Ethernet APL. What we'll see there is transmitters, or what I call APL aggregators, a device that shows up as a symbol, as a single APL device, but then connects to a number of simpler devices such as push buttons or other limit switches, other discrete inputs or outputs. So in the future, it's going to take quite a number of years. I do think we will see APL becoming a prominent and pervasive technology inside of our field environments. Now at Emerson, we've thought a lot about how we would bring APL into our control systems. One of the things that you saw in my earlier diagram, and that a number of manufacturers are going to make, is an Ethernet APL switch, a device that's designed for field mounting, has those device connector parts of APL, and then the trunk technology, as it's called, coming back from that. We will support these Ethernet APL switches, but we also think we've thought of a better way and a way to really deal with what we think is going to be a mixed environment for a long time for bringing in APL signals. Today, we have a technology we use in our Delta V DCS that we call distributed charms. And what distributed charms is, and you can see a picture of it here on this chart, is it's a field-mounted junction box that contains a number of our charms or characterization modules, where each charm for each signal can bring in a different kind of signal. This was a natural to us to expand this kind of architecture to also be able to bring in an APL signal, so that instead of having to install an entirely separate kind of junction box or field switch device right next to the charms for the analog devices you still have, with one junction box, with one technology, we'll be able to bring in the complete array of signals, whether they're traditional analog signals such as 4 to 20 or new APL signals. And you'll be able to do that channel by channel. We also know that redundancy is very important to a lot of our customers in critical industries. So we've made sure that this solution is redundant all the way right down to that individual channel connection to provide just that extra layer of availability. The protocols we expect to support in our first release, in the higher priority protocols for us, are Profinet and Hard IP, but as a system vendor, we expect that over time we're going to have to support quite a number of protocols. Again, we think that there'll be a number of protocols existing in the market for a while. Now, Ethernet APL is a very hot topic at ACHEMA Pulse this year. You'll see a number of demonstrations, a number of videos with different demonstrations. We have one as Emerson. Here's a picture of what our demonstration looks like. And what we've got in this demonstration is that charm solution that I showed you earlier on the chart, tied into one of our controllers on our Delta V DCS. We have a number of field devices. We have an APL radar level transmitter and an APL digital valve positioner, and they're tied in a control loop. So we're showing how an all digital control loop, all on APL, can work. And in this case, we're using the Hard IP protocol. We think the Hard IP protocol is going to be the easiest protocol for end users to implement, because the way you configure a device, the way you look at the data from the device, all of that is going to be identical to the HART tools and displays that practically every instrument in the engineer in the world is used to seeing and working with. So we believe this will be the easiest protocol for end users to use at first to adopt to get moving with Ethernet APL. As I mentioned earlier, it's not the only protocol we think we'll support, but it will be probably the most easiest. We've also got some 4 to 20 devices plugged in there, just to illustrate what I was talking about earlier, how with a single solution with the Delta V charms, you can mix and match both new APL signals and old 4 to 20 style signals. Now, the devices coming in from APL are of course going to be much more responsive in terms of the speed of the data, the quantity of the data. We'll be able to add new features to them much more easier than we were with 4 to 20. That's going to be the big advantage of APL. So APL, a big technology for the future that's going to change the architecture of control systems and field architecture. The second technology I mentioned was cloud, and this idea of cloud becoming more popular and more deployed in OT environments. Let's take a closer look at that. If we look at just computing in general, and over the last 50 years, I've been around for a while, I've seen some of these changes. You know, we've gone through a number of different platforms all the way from when computing first started, you know, let's say in the 1970s, from mainframes through Unix workstations. And then the standard platform of really the 21st century in the late 90s was Windows on Intel machines. And that's been how automation systems are built. I don't know of an automation system today that doesn't use Wintel. And that's been the standard in the IT world as well until about 10 years ago. About 10 years ago, IT started using a lot more cloud technology and public cloud, which is centralized, highly scalable, and they're going to be accelerating their usage of this technology, as you see. Traditionally, in the automation and OT world, we have taken IT's lead and adopted technology into our world, and I think that's happening right now with cloud. Again, traditionally, there's been a separation, a connection, but a separation traditionally between the platforms that OT uses and the applications we have on these Wintel machines, such as Control or Historian or manufacturing execution systems, and those enterprise level applications that the IT world has run in the cloud environment and prior to the cloud environment in their own data centers. But what we see happening today, and you hear a lot of talk about this, described as IT-OT collaboration or IT-OT convergence, is that IT technology is making its way into more and more OT type applications. And IT organizations, as you can see from this chart, you know, the amount of investment in IT, especially in manufacturing, is always increasing as people have digital transformation programs and they look at how they can make their manufacturing more efficient. And you'll see that where they're spending their money, no surprise, is on cloud infrastructure and cloud applications. So for sure, IT is pushing hard on cloud, and for sure, IT is spending more money on developing more applications and developing more capability. And what we've seen is IT organizations beginning to directly tackle operation problems, running analytics inside the cloud, running analytics inside from cloud manufacturers or other cloud software to come down and directly tackle OT problems. Sometimes that's done maybe a little too independently from what's happening in the operational technology world from our experience, but for sure that's going on. So in addition to this idea of IT coming in and starting to pull data into the cloud and doing some OT applications themselves, the applications are moving to executing. The ones you already have are moving to executing inside the cloud. Not control. We don't see control moving for a long time. We'll talk a little bit about that in a second. But some of the other higher level, more we used to call Purdue Model Level 4 type applications, such as a data historian or data concentration, those type of applications as people are more comfortable with the cloud and are okay with the security and availability of the cloud, we see those applications being executed in a cloud environment. We also see the cloud vendors, companies such as AWS or Microsoft Azure, building some of their own cloud native solutions for data integration, data management, some of the functions that some of those software applications down at the bottom level are already doing. So the cloud guys are moving into pulling in time series and other types of data and providing analytical tools on top of that data, many times that look a lot like solutions we're more familiar with as coming from OT specific kind of vendors. Now, why is that going on? Well, let's talk about two reasons. First, let's talk about why cloud. Okay, well, cloud has many benefits, which is why the IT industry is moving strongly towards cloud technology. Once something's in the cloud, you can access it anywhere. I mean, cloud is what has enabled all these wonderful portable computers that we all carry in our pocket as a terminal to cloud devices. It can be highly secure. There's no capital investment. It's infinitely scalable. It's easy to see why the IT world is moving towards cloud. Why are the cloud guys moving towards OT? Why are the cloud guys moving to adding some of these applications? Well, when we think of IoT and collecting data, it's easy to think of industrial because that's the world we all live in. But IoT is a huge market that spans many industries. Think of all the data streaming off of cars right now, the data that will be streaming off of smart buildings, the data that streams off of even things like farms today. And what the cloud guys realize is that a core infrastructure for all of this data to collect, process, and visualize it is something that can be consistent across all these industries. And that's why we're seeing them invest heavily in cloud. So the obvious question is, where are different applications going to go? What is the right split of applications that I need to stay on-premise versus applications that could go to the cloud, or applications that might go and stay in a corporate data center? That's a good question. That's a transition we're going to see happening, and it's going to depend heavily, in many cases, on the type of process you run, and it's going to depend on your appetite and belief in the cloud and your appetite for risk. However, NMR, the chemical industry organization that I think most ACHEMA attendees would be familiar with, it's populated mostly by European, strongly German-based chemical companies. It's put together a whole document called NE175 where they talk about this architecture of the future and some of the changes that will be coming. And I think they've done a very good job of diagramming, where different functions are probably going to land. Because one of the things that they do document that I think is very true is that most customers are going to continue to want their critical base automation and critical base control functions to be able to operate without the cloud. If they lose internet connection, that their core automation inside of a plant facility can continue to operate uninterrupted. So that is in this picture that you see here from NMR. This is what they call their open architecture, or NOAA. That's the gray box, the core process control. And you can see they show it at the production plant, not running in the cloud. But then as we leave that core automation system and you see the clouds and the pink boxes, that's opening up the world for all those kinds of applications to potentially be moved to the cloud, including a number of applications that, as I mentioned earlier, we traditionally see being on-premise today, such as advanced control or a historian, as well as new applications such as centralized reliability centers. So this chart is a great picture of where some of the separation could go between on-premise and cloud, but it's also a great picture of the next topic I'm going to talk about, or the third topic, which is the enterprise OT system. Okay, we've talked about how there's going to be all new technology in the automation world. We talked about how cloud is going to be a new computing platform for many traditional OT applications. But what I'm talking about here is actually an entirely new architecture that we see evolving, or an entirely new system, really very similar to the pink boxes that you saw on the NMR chart, that, as I mentioned, I call the enterprise OT system. And this is a whole set of new capability, new sensors, new applications, targeted not at automation, but other plant operational functions. So energy management, reliability and availability are probably one of the biggest ones that we see. Enabling workflow, automating workflow for operations inside of the plant. All these kinds of applications that aren't directly automation, but are very strongly tied to operations and operations procedure. And these platforms really are trying to automate and close the loop around a lot of other functions that have been traditionally manual in the operations world. One of the big drivers and the starting point for all of this to happen is a whole new family and a whole new set of intelligent devices, typically wireless, to gather new data in those new application areas, whether it's energy consumption, equipment health parameters such as vibration, any sort of new signal type or new sensor that we'd like to have that's going to provide us data in these new application areas. And you can see a number of those kinds of applications listed down at the bottom of this chart that we, Emerson, have provided as part of our portfolio. So things such as vibration and acoustic monitoring that we can use for many applications. That data is then fed into either gateways to just move the data along, or sometimes the gateways themselves host applications, or edge computing devices. Devices mounted at the plant level. Edge computing is one of those great terms that has a lot of different definitions. For me, it means it's at the plant level, close to where the data is generated, and that ingesting that data and running software and applications right there at that plant level to analyze and drive actionable results from analyzing that data. And there's a whole new family of devices in this area. We have some of our own. Many manufacturers are making them. And of course, there's a big discussion all the time about whether data should be processed and run at the edge, at the plant level, or in the cloud, as I talked about earlier. More on that in a minute. Why are people collecting all this data? They're collecting all this data to run analytics and software, as I mentioned. This is another area we could do a whole presentation on. But to try to sum it up in one chart, this is a chart we've put together. There really are layers of analytics that have to occur. Plants are made up of very complex mechanisms, if you will, or systems that are made up from elemental components to simple assets like motors and heat exchangers, to more complex assets like a complete process unit, to looking at the entire process plant itself. Okay. There are different analytics technologies. A lot of attention has gone into machine learning and artificial intelligence techniques, where you do pattern recognition and look at sets of data without any kind of intrinsic knowledge about what the process might be doing, or what we might call first principle knowledge about what's happening in the process. From our perspective, as we go down the chain and we look at simple assets, we know the models, we know how a pump works, we have the Bernoulli equation, we know what causes cavitation, we know all those things. Okay, we don't need AI at that level. We need a simple way to implement the first principle and failure mode effects models that we know exist at those devices. Edge computing is a great way to do that, and a great way to do that in a way that that data is generated at the plant and can be supported by plant devices. As we move up into more complex systems, such as the entire plant itself, that's where the data-driven, more machine learning type technology comes into play. Because now we don't have always highly accurate models for how this very complex system works together. And these technologies, these data-driven models, provide a great way to get a model, if you have enough data, to tell you what's going on and provide correlations. So an example of doing it at the edge is, this is a device that we introduced about 1.5 years ago at Emerson that we call the AMS Asset Monitor. So here's an edge computing analytics device. It uses the CHARMS technology that I talked about before, so it can bring in all kinds of different signals, and it can directly bring in vibration signals, which is a big differentiator for it. And again, because we know the types of assets that this is going to be applied to, we've pre-built the templates and the algorithms for you inside the device, so it's a complete solution. You don't need to be a data scientist to go in and manipulate analytics tools to build your own applications in here. We've done it for you for a large number of well-known asset classes. So this is a great example of an edge device that can do edge analytics. Now, all that data, though, typically still floats up in the architecture, lands in a customer data center, more often now lands in a customer's cloud, where they're applying big data analytics and AI and machine learning and other kinds of tools that they may be supporting. They may be using tools that are supplied directly by the cloud vendor, or they may be using third-party software that's intended for this big data cloud type application stuff. One of the big issues we see, and I think a lot of people who have worked in this area and are trying to do, big data analytics, looking across an entire facility or fleets of facilities, is, okay, maybe you can get all the data in, build individual connections, but once it's there, do you end up with a data lake, or do you end up with, as the picture shows here, a data swamp? Because although you may have all the data there, unless you have clean data that you know is reliable, and unless you have the data in context, unless you really are able to compare sets of data from different data sources together in a consistent manner, you can't do what you're trying to do, which is run the analytics. So one of the common practices we've seen is, from the cloud, as I showed in my earlier chart, build individual connections to all the different OT systems, the historian, the lab system, the reliability, the CMMS, whatever it may be, pull those in. But then what happens is the data may not be at all in a usable context. And then you have to go through a transformation for every type of application that you're trying to use. And it can be as simple as things being called slightly different names from two different data sources. So the actual putting the data together in an integrated manner in a contextualized way is a core basis that you need to have before you really can start running these cloud level analytics. And this is what it looks like today. All these different OT data sources, including these edge devices with individual connections, individual security, and the poor person trying to do analytics has to go through and sort through this different data and put it all into a context that enables them to do the application that they're trying to do. That's not a sustainable model if we really expect to do analytics in a big way. The best practice is to have something that we call an OT data lake, a platform, a software environment where it's designed to pull in the data from all these different sources, not just the streaming data, but data that might be other kind of unstructured data. So it could be text, it could be pictures, it could be vibration spectrum, able to store all these different types and then apply a uniform model such as ISA 95 to provide context around all that different data. At Emerson, we've done exactly that. We have a platform that we call Plant Web Optics. In its foundation, it has Plant Web Optics Data Lake that goes and connects to those plant level historians, those plant level LIMS systems, the plant level automation systems across a fleet of facilities and pulls all that data into a contextualized ISA 95 model. Typically, we see our customers hosting this in the cloud. It doesn't have to be in the cloud. It could be in their on-premise even or in a data center, but that's the typical use because of the scale that we're talking about. You can see one of the implementations here where we're talking about 3 million data streams a second over 100 sites. That's a lot of data coming in, and so that's where you like taking advantage of the horsepower and the universal access that the cloud brings. Once we have that platform in place for the data, we're then able to run analytics on it. And we have a suite of tools, a toolbox of analytics, as well as some of these templates that I talked about earlier, where engineers, not data scientists, you just really need to be an engineer, can go in and write analytics applications on top of this unified data set. We then have mobile clients, or a mobile phone-based client that pushes the results and the actionable information to all the users in the plant so something can actually be done. Action can be taken based on the integration that's come from this data. And then this also becomes a great way to bring all the data together and then feed it into native cloud-based tools instead of building a set of individual connections. So if we look at these three technologies that I talked about today, and as I said, one of them is really more than a technology. This is a major change that we're going to see happening to the operations environment, the automation and computing environment for different operations functions. APL is going to dramatically increase that field information and really redefine the integration between automation and the field. Many of the operations applications are going to do what the IT colleagues have already done, move their applications to the cloud or start subscribing to them in a SaaS model. And driven by digital transformation and the need to improve performance, we're going to see that gray architecture continue to be installed and grow as an entirely new operations performance kind of architecture, but at a big scale and at the enterprise level. So that is what I wanted to talk to you about today. Enjoy the rest of ACHEMA Pulse, and thank you very much for your attention.